Welcome to the third part of Module 6. The learning outcomes of the third part of Module 6 are: identify the stoichiometry concept and the relevant calculations, determine the limiting and in excess reactants, and calculate the theoretical and actual yields. First, let's review some of the important concepts that you will need to understand for today's topic. Remember that 1 mole is a measuring unit and is equal to 6.022 times 10 to the 23 items. Molar mass is the mass of 1 mole of a formula unit that can be an atom, a molecule, or an ion. This value can be determined from the periodic table. The relationship between mole mass and molar mass is presented in this formula. Moles equals mass over molar mass, which can be rearranged to calculate mass or the number of moles. In part 1 of this module, we also learned how to balance chemical equations by adding numbers to make the number of elements equal in each side of the chemical reaction. In the following chemical reaction, C3H8 plus 5O2 gives 3CO2 plus 4H2O, we can obtain very important information. For instance, 1 molecule of C3H8 reacts with 5 molecules of oxygen to produce 3 molecules of CO2 and 4 molecules of water. We can replace the word molecule with mole, so we can say that 1 mole of C3H8 reacts with 5 moles of O2 to produce 3 moles of CO2 and 4 moles of water. So these numbers are called ratios. It is very important to note that these numbers don't reflect the mass, so we cannot assume that 1 gram of C3H8 reacts with 5 grams of oxygen. Finally, notice that the total mass of the reactants is 204.1 grams. The total mass of the products is also 204.1 grams. Remember that we don't destroy or create mass in chemical reactions, so whatever mass goes in as reactants, you should get out as products. This introduction leads to the definition of stoichiometry, which refers to the quantitative relationship between reactants and products. Solving problems in stoichiometry requires the use of moles in the form of mole ratios expressed in a balanced chemical equation. For example, to make water we need the following chemical reaction. 2H2 plus O2 gives 2H2O. The ratio is 2 is to 1 is to 2. This ratio indicates that the H moles will always be double the O moles. For instance, if we have 10 moles of oxygen in the reaction, then we need 20 moles of hydrogen to produce 10 moles of water. Likewise, if we have 50 moles of hydrogen, then we should have 25 moles of oxygen. Let's look at another example. C6H12O6 plus 6O2 gives 6CO2 plus 6H2O. The ratio between C6H12O6 and CO2 is 1 is to 6. So 1 mole of glucose should produce 6 moles of carbon dioxide. The problem may be presented as: how many moles of carbon dioxide will be produced by the complete reaction of 2 moles of glucose according to the following equation. C6H12O6 plus 6O2 gives 6CO2 plus 6H2O. The ratio is 1 is to 6. To solve this question and determine the moles of CO2, we convert the ratio to a fraction. In using the fraction, you put what you want on top and what you have on the bottom. So in this example, we want to know the number of moles for carbon dioxide, so we put the 6 on top. And we have the moles of glucose, so we put 1 on the bottom. Thus, we get 12 moles of CO2. Sometimes things get more complicated, therefore the best way to solve these questions is by using the following strategy. First, we write the balanced chemical equation. Then we draw a table to determine the ratio for the molecules and calculate the moles. Let's look at a more complicated example. The balanced equation is provided. We need to calculate the number of moles of potassium dichromate, which is K2Cr2O7. That will react with 2 moles of potassium iodide, Ki. Although the chemical reaction involves many molecules, we only need to focus on the 2 molecules, potassium dichromate and potassium iodide. To solve this question, let's draw the table, and we'll write the ratio 1:6. We have 2 moles of Ki, so 2 times what we want, which is the potassium dichromate, over what we have, the potassium iodide, gives 0.33 moles. The second question is asking to calculate the number of moles of iodine, I2, that will be produced from 2 moles of potassium iodide. Again, we ignore the other molecules in the reaction and use only the relevant molecules. So, draw the table and write the ratio 6:3. So, 2 times 3 over 6 equals 1 mole. Now, what if the question is asking to determine the mass of the element? We use a similar table, but we add another row to it. Example: what mass of hydrogen can be produced by reacting 6 moles of aluminium with hydrochloric acid? The balanced equation is 2Al plus 6HCl gives 2AlCl3 plus 3H2. The first row of the table represents the mass. The second row is for the number of moles. The plan to solve this type of question is to determine the number of moles for the element from the ratio first. Then we determine the molar mass from the periodic table. Then we can calculate the mass as we have the moles and the molar mass. So mass is equal to moles times molar mass. The ratio is 2:3. We have 6 moles of aluminium, so 6 times 3 over 2 gives 9 moles of hydrogen. Add that information to the table. The molar mass of H2 is 2.016 grams per mole, so the mass is 18 grams. Let's check that we did the right calculation. The mole ratio for the hydrogen is 3, and for aluminium it's 2, so you'd expect to see more moles of hydrogen than aluminium, and this is achieved, so the calculation should be correct. Let's look at another example. What mass of carbon dioxide is produced by the complete combustion of 100 grams of a hydrocarbon pentane, which is C5H12? The balanced equation is C5H12 plus 8O2 gives 5CO2 plus 6H2O. In this question, we don't have the number of moles, but we do have the mass. Remember that we cannot work with mass using the equation ratio. Thus, we need to calculate the number of moles for the compound first. To do that, we need to calculate the molar mass from the periodic table. Let's draw our working table, and we have moles of C2H12 is equal to mass over molar mass. The molar mass is 72.15 grams per mole, So the moles is 1.39. Let's add this information to the table. The ratio is 1:5, so the number of moles for CO2 is 6.95. Let's add this information to the table. Now, using the molar mass of CO2, we can calculate the mass of the compound, which is 306 grams. Let's check that we did the right calculation. The mole ratio for the CO2 is 5, and for the C5H12 it is 1. So you'd expect to see more moles for CO2 than C5H12. And this is achieved, so the calculation should be correct. Let us now study limiting reactants and yield calculations. In many chemical processes, the quantities of the reactants used are not equal, so one reactant will run out before the others do. The amount of the products formed in such a case depends on the reactant that runs out first. This reactant is called the limiting reactant, as it limits the amount of product that can be formed. To understand the concept of limiting reactant, let's look at two analogies. To prepare a cheese sandwich, you need 2 pieces of toast and 1 slice of cheese. Say you have 40 slices of bread and 50 slices of cheese. You will only be able to prepare 20 sandwiches, as your bread will run out first. The toast is the limiting agent in this case, because it is finished and you are not able to make any more cheese sandwiches. The cheese is the remaining agent, or what we call the in excess reagent, as you still have 30 slices left. Another example is to assemble a bicycle you need 2 wheels and 1 frame. Using 80 wheels and 50 frames, you can only build 40 bicycles, as you need 2 wheels for each bicycle. Therefore, the wheels will run out first, so this is the limiting agent, and you still have 10 frames left, so this is the remaining agent. The same concept applies in chemical reactions. When you don't have equal amounts of reactants, then one reactant will run out first, and this will stop the chemical reaction, and it is called the limiting reactant. The other reactant that is still available is called the remaining reactant, or the in excess reactant. It is also very important to consider the ratio of the molecules. Let's work on some examples. How many moles of HCl can be produced by reacting 4 moles of hydrogen gas and 3.5 moles of Cl2? And which compound is the limiting reactant? The balanced equation is H2 plus Cl2 gives 2HCl. The ratio of H2 to Cl2 is 1:1. For 4 moles of hydrogen gas and 3.5 moles of chlorine gas, the chlorine gas is the limiting reactant. Therefore, Cl2 will determine how much HCl is produced in the reaction. The ratio of Cl2 to HCl is 1:2. The moles of HCl that can be produced is 2 times 3.5 moles, which gives 7 moles. What if we take this example further and ask how much H2 remains at the end of the reaction? This question might seem difficult at first, but always remember the bicycle example. We had 80 wheels and 50 frames. We were able to assemble 40 bikes, so we had 10 frames left. The same concept applies here. So after the remaining reactant is consumed, we calculate how much of the in excess reactant is left. To do that, we simply subtract the number of moles that reacted from the number of moles that we started with. The answer shows the moles remaining after the reaction is stopped. As the ratio is 1:1, then 3.5 moles of hydrogen gas reacted with 3.5 moles of chlorine gas. So the remaining moles of hydrogen gas are 4 minus 3.5 equals 0.5 moles. You might get a more complicated question. For instance, how many moles of Fe3O4 can be obtained by reacting 16.8 grams of Fe with 10 grams of H2O? Which substance is the limiting reactant and which is in excess? The balanced equation is given. You are given the mass of reactants in this example, and you can't determine the limiting reactant from that. To solve this question, you need to calculate the moles of reactant first by using the molar mass. After that, you need to consider the ratio to determine which substance is the limiting reactant and which is the remaining. Then, you can use the limiting reactant to predict how much will be produced in the products. First, let's calculate the moles of iron. 16.8 grams over 55.85 grams per mole gives 0.301 moles. How about the moles of water? 10 grams over 18 grams per mole gives 0.556 moles. Now consider the coefficient from the balanced chemical reaction. Fe equals 0.301 over 3 gives 1, and H2O 0.556 over 4 gives 0.139. The smaller number belongs to iron, and it is the limiting reactant in this example. Now we can use our table to determine how many moles of Fe3O4 will be produced in the reaction. We calculated the moles of iron in the previous step, so we can add this information to the table. The ratio is 3:1. So 0.1 moles of Fe3O4 is produced. Let's determine how much of the in excess reactant is left. The in excess reactant is water in this example. We started with 0.556 moles of water and 0.301 moles of iron. Remember that we need to take the molar coefficient into consideration. The moles of water remaining will be 0.556 moles minus 4 over 3 times 0.301, which gives 0.155 moles. Another example. How many grams of silver bromide, which is AgBr, can be found when solutions containing 50 grams of magnesium bromide and 100 grams of silver nitrate are mixed together? How many grams of excess reactant remains unreacted? The balanced equation is MgBr2 plus 2AgNO3 gives 2AgBr plus MgNO3 2. The moles of MgBr2 is 50 grams over 184.1 grams per mole gives 0.279 moles. Let's calculate the moles of silver nitrate. 100 grams over 169.9 grams per mole gives 0.589 moles. We must consider the stoichiometric coefficients of magnesium bromide and silver nitrate. Magnesium bromide is 0.272 over 1 equals 0.272, and silver nitrate 0.589 over 2 equals 0.295. Therefore, magnesium bromide is the limiting reactant, and silver nitrate is in excess. Now we use our table to determine how many moles of silver bromide will be produced. The ratio is 1:2, so 0.544 moles of silver bromide are produced. Using the molar mass, you can get 102 grams as the mass. To calculate the mass of the in excess reactant, we need to calculate the remaining moles first. We started with 0.589 moles minus 2 times 0.275 moles, so we are left with 0.45 moles at the end. Using the molar mass, we can get 7.7 grams of silver nitrate remaining. The quantity of the products we calculate from chemical equations is called the theoretical yield, which represents the maximum yield, 100%, of the product. The actual yield is the amount of product that we finally obtain from the chemical reaction, and in reality, it is often less than the theoretical yield. To see how efficient the reaction is, we calculate the percent yield, which is the ratio of the actual yield to the theoretical yield. Let's look at another example. Carbon tetrachloride was prepared by reacting 100 grams of carbon disulfide and 100 grams of chlorine. Calculate the percent yield if 65 grams of carbon tetrachloride was obtained from the reaction. So the example is asking to determine the percent yield. The question mentioned that we obtained 65 grams of the product, so this implies that this is the actual yield, and we will need to calculate the theoretical yield. To do that, we follow the same steps as we did in the previous example. The balanced equation is CS2 plus 3Cl2 gives CCl4 plus S2Cl2. First, we need to determine the limiting reactant. The number of moles for CS2 is 100 grams over 76.15 grams per mole gives 1.31 moles. The number of moles of Cl2 is 100 grams over 70.9 grams per mole gives 1.41 moles. Before we decide which one is the limiting reactant, we need to take the coefficient into consideration. So, CS2 equals 1.31 over 1 gives 1.31, and Cl2, 1.41 over 3, gives 0.47. So the limiting reactant in this example is Cl2. Now we can determine the theoretical yield for carbon tetrachloride by using our table. As per the calculation before, there are 1.41 moles of Cl2. The ratio is 3 to 1, so this means that we have 0.47 moles of carbon tetrachloride. Using the molar mass, we calculate the mass, which is 72.4 grams. So according to the equation, we should have obtained 72.4 grams. However, we actually obtained only 65 grams. So to calculate the percent yield, we divide the actual yield by the theoretical yield and multiply it by 100%. In this case, 65.0 grams over 72.4 grams times 100% will give 89.8%. This is the end of the Module 6 content. In the following slide, we will summarize the key points and important concepts we covered in this module. In Part 1 of Module 6, we introduced the concept of the mole and said that 1 mole of any element contains 6.022 times 10 to the 23 atoms of this element. This number is called Avogadro's number. Moles can be calculated by the formula moles equals mass over molar mass. The molar mass can be obtained from the periodic table. The formula can be rearranged to calculate the mass or the molar mass if required. After that, we investigated the empirical and molecular formula concepts and gave some examples. In Part 2 of Module 6, we introduced the chemical equations and discussed the importance of balancing those equations. We also discussed the oxidation-reduction reactions and the steps required to balance those. We finished Part 2 by discussing the oxidation number of atoms. In the third part of Module 6, we built on the previous concepts to explain the stoichiometry of chemical equations, and how we can use this concept to determine the limiting reactant. We finished the module by introducing the percent yield, which is the ratio between the actual and the theoretical yields. This is the end of Module 6. Please practice the weekly exercises in your textbook and the questions you find in your workbook. We will meet face-to-face in the tutorial sessions, and this will be your opportunity to ask any questions or seek further clarification.